Right. Hello everybody. It's Seokhyun again. Today I'm going to talk about circular motion and universal gravitation. This is a unit in the AP exam that's not necessarily covered too much. Um, as far as I'm concerned, it's only like 6% of your total score, but nevertheless it is pretty important, so let's get started. The first topic that is covered is the four types of forces that you'll see. Um, First is gravity. Although we say gravity, the technically correct term is universal gravitation, and we often know gravity. The force of gravity is the mass times the gravitational acceleration, but that's only for Earth. Gravity is actually just the force that tries to attach two big objects together. And that's why it can be applied to bigger bodies like the Earth and Sun. So that's why we say, oh, the sun holds our Earth in a circular orbit using its gravity, right? That's where that's what this gravity is talking about. And if we have two big planets with mass big M and mass small m, the force of gravity here, or force of universal gravitation, is defined as a constant g times the big M times small m over the distance squared, where the distance is the distance between the center of the two planets. Um, sometimes we use a negative sign there, but that's really just to show that gravity is an attractive force, as we probably know. Um, the Earth pulls on the apple when the apple falls, right? So it's an attractive force, so the direction is pointing towards towards the other planet, which is why we write a negative often because we try to show that it's the opposite direction of what we think it is. Um, but that's the force of gravity, and under this definition of gravity, the gravitational potential energy that we talked about slightly shifts as well, because in this definition, it's just m times g times h, right? But under this definition, it becomes g times m over d. It's basically the same thing if we think about it, because the force of gravity times the distance, in which here it becomes Fg times h. Here it becomes Fg times h, which is d, because that's the distance between the two planets, and that's what defines, potential energy. That kind of goes away. So that's the gravitational potential energy of that system basically forms. Um, Obviously, there's a lot more to why this is the potential energy. Um, we don't really have to go to that. It gets complicated. It gets overly complicated. This is all you really need to know, in my opinion, if you're just gonna study physics for the sake of taking this exam. Um, and there's something called weak and strong forces. These are actually intermolecular forces that are present between the molecules. You probably have seen this in chemistry, if you took chemistry ever. Um, and really, the exam doesn't really cover this. It's there for you to know that, oh, these are there, um, but they're not really covered. We don't really do any calculations with them, so they're just there. They're intermolecular forces, um, that act in a more smaller scale than gravity and stuff like that. And we get to electromagnetic forces. Um, Here we're gonna get into a tiny bit of ENM. Um, and we are going to talk a bit about the potential energy um, of the system as of the electromagnetic potential energy. I think we will talk about a tiny bit as well. Um, so for electromagnetic forces, if you have studied chemistry or anything like that, you know that likes repel each other for this one. So if you have two electrons here, they are going to repel each other. But we want to know the strength of which the two electrons are repelling each other. And that's known as Coulomb's law, which states that the force of the two electrons pushing against each other is the Coulomb's constant K. It's different from the spring constant. It's something called Coulomb's constant. It's 9.0 times 10 to the 9, I believe. It's K times the size of that electron Q1, size of that Q2, over the distance squared. It's pretty similar to the force of gravity. The only difference is that these two are pushing against each other and gravity are pulling towards each other. That's the difference that those two forces have. So similarly, the potential energy due to the electromagnetic force is K times Q1 times Q2 over R. Um, that's the potential energy if the two electrons are a distance are apart with Q1 with charges Q1 and Q2. Um, there's something called electric potential. Um, which basically denotes the strength of the electric field due to these electrons. Um, honestly, I don't think that it's worthwhile covering that in this video. I will later, if I do have the chance to do so, make a separate video on ENM and cover all the topics there. But I believe that for at least for this exam, AP Physics 1 doesn't really cover ENM. It does have Coulomb's law, I believe. You do need to know that. But electric potential, circuit analysis, that type of stuff you don't really need to know for this exam. So we're not going to learn this too much here. But just note the electric potential energy and Coulomb's law, they're useful to know. And the reason why gravity, weak forces, electromagnetic forces, and strong forces are in this order are because of the strengths. So gravity is weaker than weak forces, and weak forces are weaker than electromagnetic forces, and strong forces are the strongest force that we know. So that's why these are written in this order. Just keep that in mind. And the second topic that we're going to cover here is circular motion and kind of analyzing what's going on there. So as I mentioned above, when the Earth is pulled by the sun, we say that gravity pulls Earth into the sun's orbit, right? So why this is true is because the Earth is inherently flying at a velocity v, right? It's going at some velocity v initially, and the sun starts to grab on it perpendicularly to that velocity. What's going to happen here is that the velocity isn't going to change, although acceleration is applied. Acceleration can also be used to change the direction of the moving object, which is what happens here. The V is going to get tilted slightly, and it's going to go slightly in this direction, and this is going to continue to happen and ultimately make a circle. That's why circular motion and gravitation are closely linked together, is because gravitation often causes circular motion. But that's there. But a few things to note about circular motion. One, you always need, always, you need to have a force pointing towards the center of the orbit. Because circular motion, it doesn't always have to be planets. But always, you need to have some sort of a force pointing towards the center of the orbit, of the circular orbit. The strength and this kind of force, right, is going to cause this object to start spinning at some velocity v. And now the v is always, always, always perpendicular to the force. So it's going to be tangent to the circular orbit. This is mostly and always. If it's pointing that way, once we start pulling it, it's going to become perpendicular and it's going to start going into circular orbit. That's normally what's going to happen. So the v is always perpendicular to the force. Now, then we might want to link the magnitude of the velocity with the force that is pulling towards the center, which we note as the centripetal force. So the centripetal force's magnitude is going to be the mass of the object that's spinning times v squared of the object over r, which is the radius of the circular orbit. Because it's a circular orbit, there's also something called angular velocity, omega, which denotes how much this thing spins in angles and degrees per second. So it's the unit is in radians per second, and that can also be and so the centripetal force can also be noted as m times r times omega squared instead of this equation that you see here. But do not get confused because the velocity doesn't make the centripetal force. The centripetal force causes the velocity. So just because an object is spinning in a circular orbit with velocity v, that doesn't mean that a centripetal force just suddenly occurs or suddenly just pops up. That happens because there is a force that is being applied to that object. So just don't get that confused. It isn't the other way around. This is how it is. The force causes the velocity, not the velocity causing the force. Okay? Um, so yeah. The period of the orbit, which is how long it takes to spin around one time, right? We can note that as the total distance that that planet has to cover over the velocity that planet is going at, right? Which becomes 2 pi r over v, huzzah, which is 2 pi over omega. The frequency you'll sometimes see, the frequency is basically 1 over the period, which means that how many orbits can this spin in 1 second? That is 2 omega over 2 pi is v over 2 pi r. So these are the big things in circular motion that you want to know. Let's just do a quick problem to show what I mean by all of that. Let's combine all of that real quick. So we're going to take a look at an orbit of two planets where this is the center and this planet is orbiting around the center, orbiting around this planet here. And let's say the distance here is d. So we know that this planet is going in a circular orbit, and what we need to find is the centripetal force, right? The centripetal force here, the only thing that's applying on this object is the force of gravity, which would be g times m over g squared, right? And we know that this is going to be equal to the velocity that this planet is spinning at, to this equation, so we can find the velocity of which this planet is spinning around, spinning in the orbit, which is square root of g times big M over d. So that's one thing that we can know. We want to find the period of the orbit, how long it takes for this thing to spin around once. The period is 2 pi d over v, which is square root of gm over square root of d times 2 pi. And now the frequency, we just need to take the reciprocal, which becomes this. Okay? This really isn't that difficult, as you can see. Actually, I made a mistake here real quick. So that's a GMD square root of D. Um, D square root of D square root of GM. So, this is the basic idea of how we're going to solve problems that involve circular motion. We're going to find the centripetal force, and then from that we're going to find the velocity of which the object is spinning around the circular orbit, and then we're going to find the period of the orbit, and finally the frequency of the orbit. Um, Sometimes you're going to have problems where there is a component of the force that is tangent to the circle. What that means is that velocity increases over time. So the orbit's radius is going to get larger because FC is constant, but V increases, so D also has to increase to match that thing. But that's the only small thing. I'm sure we can figure that out once we get to those problems ever. But yeah, that's the gist of circular motion and universal gravitation. Thank you for listening to this short episode.